Ah, welcome to another exciting biomedical signal processing class. What I thought I would do is first give you a little rundown on my solution to homework 3, which was on the computation of the Hurst exponent, which is related to the dimension of fractality for an arbitrary curve in any dimension. So what I did was I tried a couple of different ways. This one called get chunk array gets the array one chunk at a time and then increases the size of the chunk. For each time you start with a chunk, let's say with 4 samples, you do your R divided by S computation, then you double the number of samples in your window as you traverse across all of the input data. Then you double it again, and you double it again, and you keep going until eventually you get a window size which is larger than the total number of samples on input. After you've done that, you're finished. That happens rather rapidly, especially with a finite number of samples. Get chunk array. In this case, I think we started with some ramp data, and there's only 32 elements. So that's not particularly interesting, and it does not have a known Hurst exponent. And then what I proceeded to do is I used this ramp data, and what that does is it counts from 1 to like 32, or from 0 to 32, I think it is. And then we proceed to do the analysis on it. So then my step here, which starts off at I think 2, keeps doubling with each pass. And what I like to do is just make sure that the step is less than n so I don't go off the end of the array. So I made a very simple little loop to get the R divided by S computation for a given step size on a given input array. So I'm not making copies of the input array. I'm not going to make a whole lot of extra, I'll call it new instances. And when you say get RS on step, what you're really doing is you take that scrap and you just make one of those. So if step is like 2, you're going 2 steps at a time, and then for each window of 2 samples, what you have to do is get the RS off of the scrap. So that's the range divided by the standard deviation. Okay, so to get the range divided by the standard deviation, what I did was I kept a running total of the deviation sum. That's the actual value minus the mean. And as I do that, if the deviation sum is greater than the max, then I store it as the max. If it's less than the min, then I store it as the min, because I need the range. That's the difference between the max and the min for every single window as the window traverses along the samples. So then I get this R divided by S computation by computing the standard deviation, and then I proceed to return it. So that's the standard deviation of D, where D is the data coming in. So I've got the standard deviation on my windowed sample, I got the minimum and the maximum on the windowed sample, and now I've got R divided by S for that windowed sample. What I'm going to do for that windowed sample is store the R over S, and I'm going to take its average for all the R over S's, and that'll be the R over S for that particular size window. Then I'm going to grow the window and do the RS computation again. So RS is going to give me a field of points, and through those points I'm going to draw a line. And that line is going to give me a slope of a curve, and that curve is what I'm really interested in, that slope, because that's what I'm going to use for my Hurst exponent. So some people kind of, I guess, didn't understand the algorithm or something. I'm not sure. So anyways, here it is. Here's my solution for the ramp. And it gives me a Hurst exponent, which is not particularly remarkable because we don't really know what it should be. I used polyfit to fit my my data, And so now what I can do is I can increase n. Let's make n something larger, like I'll use integral powers of 2 because I keep doubling everything in size, so that just seems to make sense to me. And what we'll do is we'll use Brownian motion, and that Brownian motion is the same Brownian motion that we demonstrated in class, which is obtained by taking a random number and summing the random numbers as you go, and then subtracting off the mean so that the Brownian motion has 0 DC component. So I wanted Brownian motion to be centered about the y-axis. This is called mean reverting Brownian motion. So then I ran that, and it looks like we've got a Hurst exponent of about 1 or thereabouts. And these are you know, the sorts of things you might like to run more than once. I suppose you could even increase n. You could probably make n with an integral power of 2 by taking a number like 1 and shifting it to the left and giving it a number like 20. So that would be 2 to the 20. And that would be an integral power of 2. And so then you could run it again. That might take a while. No, not too long. And you can see even for large numbers we're getting pretty close to a number that looks like 1. So that's kind of an interesting test of how things might be working here. We could try this instead of with Brownian motion, we could try it with unit random data. So here's some random data. Do it again. And random data is giving me a number like 0.5. And so that's kind of an interesting artifact too. Now your question is, you know, how do I know if it's right? And the answer is, well, you can check with literature. There's a whole bunch of it, and a lot of it tabulates the Hurst exponent. Give you an example. If you go online and you look at, like, I don't know, the fractal list that comes out of Wiki. Here's a list of fractals by Hausdorff-Besicovitch dimension. Dear Wikipedia, we want money. Oh, well, that's very swell. What? One time monthly? So this is begging for bucks now? Well, that's rude. I actually came here to do work, not give you money. Now it's in Italian. I'm very sorry. I clicked wrong. So here are these different sorts of curves, and then you can find out what their Hausdorff-Besicovitch dimension is. Here's a set. There's another set. Here's an interesting looking set. They call this the Fibonacci word fractal for whatever reason. These names, people just make them up. But once they make them up, they stick. So the inventors of these fractals kind of make them up. It's like, for example, this one here, I was using this for antenna design. So I was making a fractal antenna pattern to see if we could transmit radiation from one point to the other, because I modified it a little bit to make it look like a Yagi antenna. I figured it was a fractal Yagi, so I called it a Fraggy. Just make up a name, it's okay. Nobody seems to care. But it's based in the VSIC fractal. And so there's all these different things that you can do to estimate fractal computations. I'll give you a real nice example. If you take something like this. Oh no, more begging? Stop with the begging. Why is it doing this to me? Stop. Stop the begging. You can take an image and you can save it as an image, as a GIF image, let's say, and then you can do the computation directly off the GIF image, although in this case it's an SVG image, so that does me no good. You'd probably have to do a screen capture to convert it to a bitmap, or maybe there's an easier way to do it. But if you've got a bitmap of your fractal image, you can do a direct examination of the length of the curve by taking grids and then decreasing the grids in size and seeing how the length of the curve increases. So that's an interesting experiment which we can run, but it's an experiment based in image processing, which is a little bit beyond the scope of this course. Just a little bit. Not a lot, but a little bit. And so I have a mechanism for actually doing just that in place, but I think it's probably better that I not distract the class with it, and we'll just stick to the one dimension. So that's kind of where I was going with it. So now we have this lovely little system, right? And it enables us to do an analysis. That is, to what we'll call do a fractal analysis. Now, fractal analysis means to do some sort of analysis on fractals, whether or not you're getting the Hurst exponent or a fractal dimension, or you're getting standard deviations, or you're looking at frequency as a function of time. Those are all considered part of what's called fractal analysis. And that's kind of an interesting idea, because when we did analysis prior to this, we did what's called Fourier analysis. And with Fourier analysis, all we really cared about was the frequency content. Now, as it happens, frequency content for real signals changes as a function of time, right? Because why? Because signals don't start at time equal minus infinity, and signals don't end at time equals plus infinity. Sine waves don't go on forever, but everything that an FFT does, a Fourier transform does, it makes the assumption that the signal starts at time equals minus infinity and ends at time equals plus infinity, which means it makes an assumption which is patently wrong, right? Because no signal starts at time equals minus infinity and ends at time equal plus infinity. And when somebody says we'll make that assumption, and you know the assumption is patently wrong, you should say, Professor Lyon, your assumptions suck. And I say, yes, they do. But we can change the assumptions, okay? And then if we change the assumptions, then we change the problem that we're attempting to solve. And so one of the things that I know that happens is that events have finite time. Almost all events have finite time. Events start, events last, and then events end. That is the nature of the real world, right? So when we think about real world events, we start to think about how we can do a Fourier transform not from time equals minus infinity to time equals plus infinity as the integral would suggest. Instead, we say, how about we do a short time Fourier transform? And now we're changing frequency as a function of time because events occur over finite periods of time. And that is a far more sensible assumption. So we started with an unreasonable assumption, and now we're going to try and make what I would call a slightly more reasonable assumption. And in the process of doing that, I introduce you to my good personal friend, the spectrogram. Which is in spectrogram frame in the sound package. And I'm running spectrogram.main. Spectrogram.main. And first thing it does is it opens up with this lovely little interface. Now, underneath is a little oscilloscope, and it's using the right-hand slide bars to change the amplitude. And it's using this fictitious little thing in the lower corner. I don't know if you can see it, but it says 10 volts per division, right? And as you scroll up, it changes the magnitude. Obviously, voltage is not a meaningful thing, but it's trying to be an oscilloscope. And then if you scroll at the top, it changes the time base. And now it's showing you 10 milliseconds per division. Now that actually is meaningful. And when you look at these two different peaks, what you're really looking at is a Fourier transform representation of a sine wave. And the sine wave is giving you the real part and the imaginary part in frequency space. So this has now become more like a spectrograph instead of a oscillogram. It's a spectrogram. This here changes the, I'll call it horizontal, what is it called? The vertical position. Vertical position. And this here down at the bottom changes the horizontal position. So what I'll do here is I'm going to record some audio. And I can do that. Here's a little record button. And let's see what that sine wave looks like now. And there it is. There's the sine wave. And now what we can do is we can use our little oscilloscope to determine the frequency of the sound wave. Right? That's a good idea, right? So here it says it's 1 millisecond per division. That's 1 millisecond. That's 2 milliseconds, almost. So if you figure that from peak to peak it's 2 milliseconds, that's 2 1,000ths of a second. And now I'll use the only calculator which I like, and it's this one here. And so if I take 2 divided by 1, 1, 2, 3, I get this number, which I can then invert, and it says it's a 500 hertz tone. Fair enough. And what does a 500 hertz tone sound like? Apparently this isn't playing. Let's try and record something and see if that works. Oh, there it goes. I can hear it now. Interestingly enough, it seems to have thrown a little exception. Is that me that's playing that?
All the monitors are going crazy. That's probably me.
Oh, that's you?
Yeah.
Oh, I thought it was me playing that. I was like, where's that sound coming from?
I thought it was that too. Apparently it wasn't.
Do, re, mi, fa, sol, la, ti, do. Let's see if this works. So now it's working. Okay, good deal. So here's the, I'll call it voltage as a function of time, right? And what we can do is we can compress the time base a little bit so you can see a little bit more of it. And then what we'll do is we'll shrink it down, and there's like my voice. And what we can do is sort of say do, re, mi, fa, sol, la, ti, do, and you can kind of see the different note events coming through. So we have a visual representation as well as an audio representation. But now let's see if we can do a short time Fourier analysis, also known as a spectrogram. So we'll hit done, and we'll go and we'll do a log scale of the power spectral density, and we'll hit create and see what happens. And there it is, do, re, mi, fa, sol, la, ti, do. We see what's called the harmonic content of the input signal as a function of time. And one of the things that I think is very important is that there are note events clearly delineated, that notes do not begin at time equals minus infinity and end at equals time plus infinity. So what we need to do is we need to take a window in time, take a finite number of samples, run the Fourier transform on those samples, and then depict visually the harmonic content of the input signal. Right? So what has happened here is we became constrained by a couple of parameters, right? Engineering constraints, practical engineering constraints. First, basic engineering constraint. The signal had to be digitized. Digitized signals have been quantized. Digitized signals have been sampled. That's the nature of digitization. So what does this mean? We first need to know the sample rate. Okay, I'm here to tell you the sample rate is 8 kilohertz. The second thing we need to know is we need to know the number of quantization levels. Okay, I'm here to tell you the quantization level number is 256. So it's not particularly good audio. It's what I would call voice grade audio. Right? 1 byte per sample, 8,000 samples per second. What does Nyquist tell us about our sample rate in terms of the maximum possible frequency that we can represent? Oops. It's half, right? So the maximum possible frequency you can represent is 4 kilohertz. And what do we see here on the right-hand side? We see a scale that goes from 0 to 4 kilohertz. How about that? Good deal, right? So that's exactly what you would expect. Now, the other thing is, if you take only 256 different possible samples in your window, because you're doing a short time Fourier transform, you're able to isolate note events within the 256 element window. But wait, the sample rate is 8 kilohertz. So what does that mean? It means that in a 256 window sample, I can isolate note events which are 256 samples divided by 8 kilohertz in length. So now I'm going to take out my world's favorite calculator, because it's the only one I know how to use. The other ones are too complicated. Ah, crap, I can't get it. Wait, it's got to be in here somewhere. Calculator. Oh, it's not in here. I got to start it again? Okay, calculator. Calculator. Here's the calculator. Oh, it's looking complicated again. Okay, it doesn't matter. 256 divided by 8,000 samples per second is 0.032 seconds. And I can invert this, and it says I am able to isolate events as short as 1/30th of a second. So note events that are faster than 1/30th of a second will not be isolated. That's key. As a matter of fact, because of Nyquist, one thing I can tell you is I would really like it if my note events occurred no faster than 15 times per second. What does this mean to me, the guitarist? It means I cannot be Jimi Hendrix playing faster than 15 notes per second, which I think Jimi Hendrix could probably do, but which I can't do, so I'm okay. And if I'm playing on my harmonica, I'm totally fine. So as a result, I'm thinking 1/30th of a second is a reasonable, 30 window samples per second for analysis is a perfectly reasonable number to come up with. But you can adjust it. All of that's adjustable. Does everybody sort of understand the difference between the sample rate and the size of the window in a short time Fourier transform? They're different, right? Sampling at 8,000 samples per second is fine, but with a short time Fourier transform, you've got a window of 256 samples in my example here, which means that I'm only sampling events that happen in in more than 1/30th of a second. Hopefully, you get 2 samples in it, you want them to happen over 1/15th of a second. Now, here's the adjustment. You can change the window size. So if you wanted to, you could make it so that window size is way smaller. But look at the trade-off. Suppose I told you, okay, let's change the window size. We'll make it 64. Fair enough. So now what we'll do is we'll create a new recording. I don't know if I have to do a new one. Maybe I can use the old one and see what that looks like. And there we go. So now what do we see? Very wide bands, only 64 of them. So now the frequency space has been divided into 64 different subsections. And so what that means is in the range from 0 to 4 kilohertz, I have a coarse quantization of frequency into only 64 chunks. Aha! So if you took 4 kilohertz and divided it by 64 little chunks, you would get a number Where's my calculator again? I gotta do the starting thing again? Calc. I keep doing this with the calculator. It's gonna drive me crazy. Here it is. So now I've got 4 kilohertz. I divide it by 64 little buckets, and what I find is each bucket represents 62 hertz. But before I had 256 buckets. So I had 400 kilohertz divided by 256, and so now I had 15 hertz. So that's a big difference, right? Because prior to this I had like 40 hertz, now I have 15 hertz. Well, let me tell you something, 40 hertz could be the difference between a sharp and a flat when you're dealing with music, easily. In fact, for the lower frequencies it could be even a difference in whole notes, since we're evenly quantizing the scale across all frequencies. So if you go up 40 hertz, well, if you're at 40 hertz and then you go up 40 hertz, you're at 80 hertz, you just went up an octave. So you're a whole octave off because you went to a very, I'll call it, narrow window, right? 64 samples is a narrow window. So now you've intuitively discovered with our little experiment is the difference between precision in time and precision in frequency. You can have one, but you can't have the other. And if you remember your physics, right? Heisenberg uncertainty principle says you can have precision in position or you can have precision in momentum, but you cannot have both because they're inversely related with respect to one another. Same exact thing when you're doing frequency analysis with a short time Fourier transform. It's the Heisenberg uncertainty principle for Fourier transforms. How cool is that? So it all kind of relates back. Now, to put too fine a point on it, I can take the two different spectrograms and I can compare them side by side. And you can definitely see a big difference in terms of frequency resolution. But you can also see a difference between temporal resolution. Right? Those bands, those subbands are very narrow over here on the right where you see the 256 samples. Over here on the left we have 64 samples. That's 64 buckets for frequency. Big difference. So when you go to decide how to do the spectrogram, you have to decide what kind of material you're attempting to do analysis on. This is so important. If what you're trying to analyze is a fast-playing guitar player, that's a completely different thing than if what you're trying to analyze is an electronic cardiogram. An electronic cardiogram, ECG some people call it, well, that could be analyzed with perhaps 256 samples per second. Not a lot of samples. But when you do audio, you really want to go thousands and thousands of samples per second. And if you're doing a high-performance, very fast player of some sort of guitar solo with lots and lots of notes, then you want to have a fairly narrow window. But if you have a narrow window, then you've lost some of your frequency resolution. How do you make up for that loss of frequency resolution? Let's say you want to go to 1/30th of a second, as I did in my sample. What can you possibly do to improve your frequency resolution? Yeah, increase your sample rate. So if I have a higher sample rate, then I can go and squeeze more frequency buckets into that tiny little window of a sample, and now all of a sudden I can develop a higher precision spectrogram for my application. So your application might not be something that works well with 8 kilohertz sampling. That's voice grade sampling. Voice grade sampling is just not good for certain things. For other things it's just fine. So it really depends on your application. How's that for a demo and an explanation? Good, right? Let's try. You see, so far you've heard my voice, right? That's called solfeggio, do, re, mi, fa, sol, la, ti, do. It's a basic major scale. But even though it is a biological signal, because it's my voice and it comes from a biological source. There are other biological signals that maybe make more of a difference to us. So let's try a different biological signal. Let's look at the source of it. We're going to synthesize a biological signal, and the signal I want to synthesize comes from a package called bio. And in the bio package, and this is already in your course code, there's an EKG is the German spelling. It's ECG for the English spelling, electrocardiogram. So let's run an electrocardiogram. I must be doing something terribly wrong here. So this was working just fine before. It really was. Just bear with me a minute. Sometimes demos don't always work as advertised. I'm just going to check out my notes here. Generate the ECG, it says. Oh, application, of course. Run. Let's see if that works. Yep. So now what we'll do is generate ECG. We'll hit generate, and voila. It's an electrocardiogram. And it even gives us the data, which is kind of cool. And what we can do with this data is we can save the data, and we can save it as a CSV file, which is right here. We'll replace the existing one, that's fine. And it says here it generated 65,772 rows. And what we can do is we can look at the parameters. And the parameters give us the ability to change frequency, they can change plot area, they can change speed, we can alter the human heart rate, we can change all kinds of things about noise. Here we have additive noise, we can make it very noisy. We can change the sample frequency, we can change the spectra, we can change other things. These are parameters that people are able to identify when they do an ECG. So we have a completely parameterized waveform. I've been saved. So let's see. I'm going to run my favorite editor. You can use Notepad if you like, but I'm going to use Emacs. And there's my data. And now let's do a little bit of an analysis on the data. I'll bring up my my very good friend, the calculator, and we'll look at this time. He says he's giving me time and the voltage. So let's take this time, 0.003900625, and then we'll invert it, and what do we see? 256. How cool is that? Invert it again, hit plus, hit equals, and it's 0.0078125, and that's the next sample. So what he's doing, it's pretty clear, he's sampling once every 256th of a second, and then he's giving us the decimal version of 1 over 256 as a time. But in fact, if we know the sample rate, we don't really need it. It doesn't add anything to us, because anything to the computation, because if you keep going, you can see all of these numbers are going to be there. 0.0039065 is exactly the same as here. So it turns out, if you know the sample rate, you really don't need to know the time at each sample. Right, that doesn't add anything, but you have to know the sample rate. Let's see, I got the voltage as a function of time, so that's good. Let's see if we can take a look at this voltage as a function of time. It seems like it's ranging from -1 to +1, slightly more than +1. So then I thought to myself, wow, what an interesting thing. what if we did the spectrogram on the electrocardiogram? Wouldn't that be fun? And then I said, geez, I could do that. And then I thought, but why should I? I have students. Ooh. And therein lies the rub. And then I said to somebody, oh, what would you like to do for your next homework assignment? And I got a, oh, we should get a biological signal and we should do analysis. And I thought, yes, that's a good idea. What a swell idea. So then I think, I need a midterm. I think I might have a midterm, so my midterm senses are tingling. So how about this? Now that you know how to generate ECG data, now that you know how to do a spectrogram and you can see what it looks like and you understand the trade-offs that occur between sample rate and window size, I think it would be really good if you guys did the spectrogram analysis on the electrocardiogram as we have generated it. So you can regenerate it on your own, or you can use the data that we've got here, and we can hand that in as a a midterm result for next week. Doesn't that sound like fun? Spectrogram analysis, as we may have hopefully demoed for you. So what do you think of that as a midterm? Yeah, do a spectrogram analysis on an EKG, or an ECG as they say. I'm so used to calling it EKG because that's what I think Dr. Kildare called it in General Hospital or something. So it's one of those things where I thought we would have fun doing it and we'd learn something in the process. So what would you do to approach this problem? How would you approach this problem?
Figure out how to generate ECG signal.
Well, we already got that, right? Here's my signal. I already made an intimation that you probably don't need the time part or the peak part. You just need the voltage as a function of time. So it's just the middle section. It's coming in as a comma-separated value file. What reads comma-separated value files anyway? File reader. Okay, fair enough. Let's see now. I think I have something here that does that. I believe it's called Microsoft Excel. Doesn't Microsoft Excel read these things? Open? What if you just open it? Does Microsoft Excel open? Oh yeah, see, it knows how to read that. So if you don't want something like the time, right, you can like delete it, right? And if you don't want the peak part, you can just delete that, right? And if you didn't need this row, which just says voltage, you could delete that, right? And then if you wanted to not to put too fine a point on it, you could probably plot it or something just to make sure you know what you've got. Not exactly sure what I'm doing. It seems like I'm going a little too far with this. It's supposed to go to 65,536. Let's just go to 63,000. That's enough. Let's insert a chart. Let's see. How does one do this? Scatter, scatter, and then this doesn't look so very good. I think my scatter chart isn't good. There must be another way to do that. You all know how to use Excel? It's one of those things I don't use typically. Oh, maybe I'm doing something terribly wrong. Should I have just gone back to here and just click A? Oh, and then click on charts and then scatter, isn't that right? or line.
You have a lot of points.
Let's try the line. It's too many points, huh? Excel has trouble with that? Yeah, it's just too many points. I think we have to do it so that there's only like, I don't know, 1 second worth of data or something. So let's just stop at 256 and see what a second worth of data looks like. So we'll do insert and then chart, line, or scatter, I guess could be used this time. Scatter. Oh, alright. So that's sort of looking like the original data, more or less. Just don't smush it all in together. So I think we have the right data here. I could probably save it as a CSV file and write a program to read it in Java, because this is not a particularly complicated file now. It's just a column of data. We know the sample rate. What about the representation of the audio signal? Because the spectrogram wants audio signals, right? Do we want to reuse the spectrogram code? Do we have to? I don't think we have to, but we certainly could. So if we wanted to, we could transmogrify this entire data file into audio and play it, right? But if you're only sampling at 256 elements, it's not going to sound, 256 samples per second doesn't sound like very much, right? Is it going to sound like a heartbeat? Maybe not, unless you want to move it, unless you want to modulate something that sounds like an oscillator. How about the data input for playing audio and for the recording of the audio? Do we have any insight into that? No? No insight at all? Really? Suppose we do the following. Let's take a little tour of how we can generate audio programmatically. We'll go into our little sound area, and we'll hit run and see if we can make an oscillator happen. So here's an oscillator. Wonder if I can hear this. Oh, here's volume. There we go. So somebody's generating audio here. So apparently you can generate audio within Java. Have we never tried that before? Does that sound like something complicated? Would it make sense to learn how to do that? I think it makes sense, sort of, more or less, somewhat. So what I'll do is I'll try and do something with an oscillator. Let's see. What would be a good way to do that? How about if we use a sine wave, take the sine wave, put it into an oscillator, and then take the oscillator and play it. I think that might be a thing to try. Here's a little oscilloscope which is used to visualize sound, and it's got the same features in it that the other one had, only this is dual trace, so we can see two traces superimposed on each other. Let's see if we can do another one. I'll try and see if I can come up with a nice simple idea behind all of this. This here is called double data, and what this double audio, and what this does is it takes simple audio data as a double precision number, and the number ranges from -1 to +1, and transcendental functions often do this too. So if you take math.sine, it ranges from -1 to +1. So math.sine is a great way to make a sine wave. Math.cosine will be a great way to make a cosine wave. And so what this does is it gives you an opportunity to go through a waveform and then proceed to realize it by either visualization using an oscilloscope or by listening to it. So you get two opportunities here to be able to, I guess you might say, validate our understanding of how these things work. I suppose that's one way to put it. So what we'll do is we'll try this this little idea that I have. Here's a thing called an oscillator, and the oscillator has this audio data, and what it can do is it can allow you to create audio with different frequency and different amounts of samples. And what it'll do is allocate the double precision audio data internally, and then it will let you play the audio data. Now, to play the audio data, what it does is it takes the audio data and encodes it in what's called a U-Law codec. And if you read the book, I think it was in chapter 5, you'll see there's a subsection in there called U-Law. U-Law is one of those codecs that's very handy because Java has a way to realize the output directly. Yeah, I think it's page 230. They show page 229, the U-Law codec concept. And if you look at, did somebody say 237? Yeah, 234, we have the U-Law codec class. And then if you go to page 237, you can see reading and writing U-Law files. So the U-Law codec is one of those things that allows you to read U-Law files and then play them. It can also let you take double precision data and play that as well. Let's see if there's a main in all of this. That was not expected. It seemed to work though, so that was cool. Here's the main. This is setting an instrument. We don't need that. This is oscillator play linear data, and we don't need sound utils to get a note number. There are all kinds of different ways to play notes. One of them is with MIDI, which is the musician's interface, digital interface. What I'm going to do in here is I'm going to get rid of this thread, and I'm not sure I should have done that. We'll try it anyway. See if it works. Now what I'm going to do is try and change the frequency. Let's double the frequency and see how we do. Oh, that worked. Good deal. So what I've done here is I've given you an API called oscillator. What oscillator will do is it'll get you different waveforms. This one's a cosine wave as linear data. And then if you call oscillator.play linear data, it'll take the linear data in and play it onto the speaker. So that's fun. So what you need to do is you need to derive a mechanism to get an array of numbers, double precision numbers, that range from -1 to +1. And you can't go beyond that. That's the constraint. So if you can create numbers that go from -1 to +1 from your ECG, then you'll be able to play them on your speaker. And I think you can probably do that, but you might have to renormalize them because I think they went to a slightly higher than 1 and maybe slightly lower than -1. So what that probably means is you'll have to find the positive max and the negative max and renormalize the data. there is an audio data, yeah, it's called double audio, and that will do renormalization for you. So if you want it, it'll get you the min, it'll get you the max, and it'll do the normalization. And that'll give you an amplitude that ranges between minus 0.98 and plus 0.98, I think, at the end of the day, which is kind of giving you a little headroom, I'll say. So if you want to, you can use double data and read in the data and then play it if you prefer. So now that you've got your data and you've got a way to sort of realize it, maybe you're ready for the spectrogram, or not. What would be the next step? Here's the U-Law codec, by the way, in case you were wondering where that's at. And he's looking for audio data. I happen to have a little section in here for audio data. And let's try this space music here. So it's reading in the audio file and then playing it. And it's also visualizing it with the little O-scope frame. Let's see, we'll use this and we'll change the I guess I have to go up and down a little bit. Oh, and left and right, of course. And then you can see the audio data coming in. Kind of a lot of data. So there's that U-Law codec. If you go to the U-Law codec, you can see it'll take double precision numbers as an array. Those double precision numbers range from -1 to +1, and you can take arbitrary signals coming in and make a new instance of the U-Law codec, and then to realize it, you can just call play, and it should just play, in theory. We can develop a little test if you like to see a test. I'll make a new Java class with that, and I'll call it test U-Law. Okay, and what we'll do is we'll make a main method, and we'll figure that it's going to play at 8,000 samples per second. So let's make 1 second of audio. So double D array equals new double double of 8,000 samples. That'll give me 1 second of audio. And then what we'll do is we'll fill it with interesting sounds. How shall we do that? A for loop, I think. For integer I equals 0 while I is less than d dot length, I plus plus. And now the question is, how shall we arrange to assign the values? How about math dot sign of I, but if I do that, I want something in radians, right? I need something like theta, whatever theta is. And so now I've got to figure out how to compute theta. Any ideas? Well, if I wanted 440 samples, 440 hertz, right? Then I would want to have a peak waveform that changes 440 times at 8 kilohertz samples. So how will I know the time as a function of my sample number? Time I can get, right? Time t is equal to, let's say, call it a double. And what will it be? We're going at 8,000 samples per second. So it's the sample number divided by like 8,000, right? So that's my time as a fraction of a second, because I only have 1 second of audio. So when I is equal to 4,000, I know that I'm at the 1/2 second mark. Is that making any sense to anyone? Am I, Mike, are you with me on this? Cool, right? So then if I said to you, I want 400 samples per second, then you know that there's going to be 400 cycles between t equals 0 and 1. Does that sort of make sense? So when t is equal to 1, I would like a number like 400. And when t is equal to 0, I guess I'll be at cycle 0. So should I use math.pi or something? Would that make sense? Double theta. I mean, I'll put it a different way. double. Double theta equals, you tell me, math.pi. Well, if I said times t, then I'll have 1 cycle when it goes to 1 second. I think pi has to be uppercase. So maybe if I multiply by 400, right, that'll be 400 cycles. Is it a sign of, don't I want 2 pi to go a whole cycle? I think it's 2. 2 times math.pi times t will give me 1 cycle as it goes to t equals 1. But somebody said we want to make 440 hertz. So if I do 440 times that, then I'll have 440 cycles in the duration between 0 and 1. Are you guys with me on this? So now I've got my double precision data. I've made my little tone. Tell me if you're lost. We're good, right? So, huh? A little lost. Okay, so put it a different way. If I told you that theta was ranging between 0 and 2 pi, you'd have no trouble telling me that you're going to draw a sine wave, right? Now if I said as t goes from 0 to 1, I'll be going to 2 pi 400 times, then it's clear that I have 400 cycles in a second, because t is ranging from 0 to 1. So what I'm trying to do here is say 440 hertz should be what I get, and then I don't know if I explained that right. Then if I make a new U-law codec, ULC equals new U-law codec dot, oh, I know, I need to put in the double data, D. Tell me I did that wrong. Cannot resolve symbol. Oh, it's got to be lowercase. L. And then ULC dot play, maybe? What does that buy me? That sort of works. Now, in theory, I should be able to go down 1 octave. And if I wanted to make sure that I had a sound that was within the plus minus 1 that we talked about, I might multiply this by 0.98. And that sounds a little low, but let's go up in frequency, 440. And that's your sine tone, 440 hertz. And if you want, you can double that in frequency, 880. 880 hertz. So what do you think of that? So, yes, sir.
I just don't understand the point I
Oh, because I wanted a little headroom for my U-Law codec. My U-Law codec does what's called companding. It gives us more headroom for low volume audio than it does for high volume audio. So it allocates more bits for the low volume audio because our ears become more sensitive to small changes at low volume than we do to small changes at high volume. So when you're listening to a jet engine, small changes at high volume are something you're relatively insensitive to. So what U-Law codecs attempt to do is they attempt to take human physiology into account during the coding, and so they allocate an exponential increase in the total number of bits. And that's the nature of companding. Now, initially, when Bell Labs came up with this back in like the 20s, they used a bunch of analog circuits to implement the companding for voice-grade audio lines. But what has happened over the years is people have come up with a mechanism to do this digitally. And so when we start to think in terms of what it is we need to do to accommodate the U-Law codec, we start to give it a little bit more headroom, especially when we're dealing with high amplitude signals like the sine wave. And so by going only to 0.98 instead of 1, we give ourselves a little bit more headroom at the top, and it doesn't sound like there's a ton of distortion going on. So we reduce the amplitude somewhat. Headroom is so important in electronics. When you are trying to play, when you're trying to wail on a guitar and into the guitar amplifier, what you're looking to do is you're looking to use your transistor not as a switch, but as an amplifier in a linear mode. Now, if you use it as a switch, like a digital design person does, the transistor goes from one supply rail to the other, and it makes square waves. But if you're trying to make a good quality amplifier, as an electrical engineer might like to do, then what you're trying to do is moderate the input current to the bipolar junction transistor so that it operates in a nice linear region. Well, within the supply rails, because if you go to the supply rails, then it's going to start to clip. Now, the reason why people say they like the tube sound, vacuum tubes, is because instead of clipping with a hard edge, vacuum tubes engage in what's known as soft clipping. So when the grid gets excited, instead of going straight to the supply rail, it gradually goes to the supply rail on the tube. So tubes give you a special sound called soft clipping, which makes it okay to take the tube amplifier and run it straight into the speaker. The speaker is an interesting device. The speaker is a paper cone that's suspended with what's called a spider around what's known as a voice coil. The voice coil oscillates inside of a magnet. Now, when you take a square wave and you start to move this paper cone, which has mass and a voice coil, with instantaneous change in position, because the square wave wants you to go from here to here without any time elapsing, then what you have is infinite force to give yourself infinite acceleration in order to be able to get the speaker to go from one place to the other. That's what happens when you pump square waves into speakers. So what happens is the speaker starts to engage in what's called a nonlinear mode of oscillation. And the voice coil jostles from one side to the other as the speaker cone starts to engage in that nonlinear wave. And then it gets stuck. And what happens when you press a little bit on the paper speaker cone is you hear the clicking of the speaker coil against the magnet. And what you have done is you have blown the speaker, because you used a transistor amplifier at high amplitude and gone from one supply rail to the other. So what people like to do is they like to use like their Marshall amp with their little vacuum tubes, and in this way they can save their speakers. So if you have a bass, let's say, and you play into a guitar amp, it's very easy to blow the speaker. I'm here to tell you. So this is like not something that I've done this, and not to my amp either. Like it's okay to do it to your own amp, but when you're doing it to other people's stuff, they get really all pissed off and everything, and then you have to kind of like replace it. And sometimes it's very hard to replace these old amps. So that's why I give myself a little headroom, both digitally and in the world of electronics, because otherwise what happens is you start blowing out electronic devices. You can do serious harm. And that's my... I know it sounds like I went off on a tangent, but because you asked and because it's so important, I thought it might be worth hearing. So that's one of those things. Give yourself a little headroom when you're working with codecs. Give yourself a little headroom when you're working with analog amplifiers. These are all part and parcel of what you need to know when you start to try and survive in the world of electronics. Now the question is, what would we do if we wanted to realize a tangent waveform? Right, tangents have like little pointy asymptotes, right? Every 90 degrees. What could I do here to protect myself from going beyond the hard limit? I mean that's easy to do, right? I can just type tangent and I'm done. Now what? See, that's going to work, right? Because it's not a syntax error. Java likes it. I just hit play and it'll go. Ooh, nasty. Nasty sound. So what can we do about that? Well, if you want to protect DI, you can guard the input if DI is greater than 0.98, then set it to 0.98. Right? And what about if DI is less than 0.98? Right? Then you can just set it to, well, we got negative. Right? Negative. Then we'll just set it. DI equals minus 0.98. So that kind of limits us. At least it gives us a little headroom. And it sounds quite a bit different too. I still don't care for the way it sounds. I could probably have used sine in here now. It'll probably still work, right? Hope so. And it does. So it's all good. So now what would happen if you wanted to visualize the sound? Right? That's good. You want to see it, right? So you need an oscilloscope. Is it the O-scope? Oscillator panel, O-scope panel. I think it's O-scope panel, isn't that right? I forget now. Oh, I think there's an oscilloscope frame, isn't there? No, maybe not. We'll try O-scope panel. And I'll just take a quick look and see if there's an example of how to use it. Because it's been a while. That's not too bad. Here it's asking me to create a frame called a closable J-frame. And add the O-scope panel to it and change the grid layout. Let's see where that's at. I'm going to look at the he's all in sound. So theoretically, in the sound package, I should be able to find the O-scope panel. And here it is. So it's right there, O-scope panel. See what I can do with it. I'm just going to take a quick looky-loo at the API. So he says here I can construct an O-scope panel with an array of double data. Well, we have that already. It says here I can just call O-scope panel.showFrame. Let's see what that buys me. Oh, so if I call O-scope panel.showFrame, it looks like it does all the work for me. So I'll go back to my test ULaw. I'll do an O-scope panel.showFrame, pass in my double precision data, and run my little program. And that sort of looks like a sine wave. Now, what we can do, because the O-scope is capable of doing a little analysis, is I guess this is not exactly right, but it's close. Let me see if I can get the there we go. 1, 2 and a fraction milliseconds per division. So calculator. What did we say? 2 milliseconds? That's 1, 2, I'll call it 2 1/4 milliseconds. 2.25 divided by 1.123 equals, now take 1 over that, and that's 444 hertz. That's pretty good. So he hasn't exactly told me, you know, with his frequency counter what the frequency is, but what I have done with my little, you know, O-scope tool is I verified in the time domain the actual frequency. What do you think of that? Good, right? We're good with that? So what would happen if I took theta and I squared it? That is a very interesting waveform, isn't it? It's a chirp. That's what they call it. The frequency is changing as a function of time. It's actually changing very rapidly. And what I should probably do is take off that 440 and see if we can see how that works. So there's the chirp, and it's taking the sine wave and increasing it in frequency as a function of time. Chirp is an analysis waveform, and it's also something people use for radar systems. It's not supposed to be something you could hear right now unless you want to change the frequency sufficiently so that it can be heard. Let's see if we can go up in frequency somewhat. Let's go to 100 times that and see if we can hear this chirp change in frequency. That's pretty cool. So you can hear rapid changes in frequency with that. It even looks cool. Chirp waveform. There you go. So now we can see the chirp changing in frequency rapidly. Isn't that cool? That's pretty cool. Chirp waveform. So What have we learned today? What did you learn in school today? Nothing. Well, you must have learned something. No. Well, didn't they tell you anything? No. It's a waste of time, but we're spending so much money. It's terrible. Don't they? Wait, tuition is at $720 a credit hour and you didn't learn anything? Yes. Okay, here's what we learned today. We learned how to synthesize audio from a function, a transcendental function. We learned how to play the audio so that we can hear it. Very important. We learned how to visualize the audio so that we can see it. All equally important. We learned how to take interesting functions like the chirp and not only realize them mathematically, but also to be able to hear them and to see them. And now they have these interesting ways in which they can be validated, right? We can now see how sweeping waveforms can come about. Let's say we'll try one that sweeps a little bit slower here. Let's see if this works any better. Yeah, that's pretty cool. Whoop, whoop, whoop. Okay, so yeah, it's getting higher in frequency as a function of time. You can almost envision what the what I would call, what's happening here is aliasing. Let's see if we can increase. Let's see, I want to decrease the time base, and there we go. And then now you can see like harmonics coming in because of the aliasing at the end. So that's kind of neat. So wouldn't it be neat if we could take these waveforms and then proceed to do a Fourier transform on them as a function of time? Wouldn't that be swell? So now you guys have gotten to the point where you're really almost ready, I think, to start to approach the midterm, right? Because you've got the audit, you got the data, you've realized it by listening to it, you've realized it by visualizing it, but what you haven't done quite yet is a frequency-based analysis. You've only done a time-based analysis, right? These oscopes really are only allowing us to visualize the audio as a function of time. Speaking of which, is it time for a break? Yeah, it's break time. So let's do a little break.